Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to show you how you derive the Henderson-Hasselbalch equation from your ice table and from basically the K expression. So let's get into this. Okay, so you all know hopefully by now about ice tables and how to use your ice table to figure out what the pH of a system is by plugging that into your expression for K and solving for X and all of that. So in this video, I'm going to show you how you can derive the equation called the Henderson-Hasselbalch equation, which makes your calculation simple. But you have to remember that the Henderson-Hasselbalch equation is only used for buffers. And it's even in those cases, it's only used when the change in the equilibrium is negligible, where basically X that you're solving for is so small that in comparison to the initial concentrations that it really doesn't make a change in the initial concentrations. So basically your initial concentrations are the equilibrium concentrations. Okay, so make sure you know that, because otherwise if you use it incorrectly, which a lot of students do, it just basically tells your teacher or your professor that you can't tell the difference between a buffer solution and a regular acid or base solution, right? So you got to remember that a buffer solution is going to have it's a weak acid and its conjugate base, or a weak base and its conjugate acid. So here I have an example of a generic buffer solution, where here I have the weak acid reacting with water to form your hydronium ion or your H plus ion, and the conjugate base here. Now, if this is just a weak acid thrown in water to react with water to balance, your Henderson-Hasselbalch equation is not going to work with that. And the reason for that is because it's not a buffer solution. It's not going to work. So you have to have both your weak acid and its conjugate base both in solution and both in large amounts, or relatively large amounts. Okay, so if you don't have that, then you can't use the Henderson-Hasselbalch equation. Okay, so recognize that. Now, so what we're going to do to derive the Henderson-Hasselbalch equation is we're going to start with our Ka expression. And the first thing I want to note is notice that the concentrations of your hydronium ion and your conjugate base and your acid, your weak acid, are all at equilibrium concentrations. So remember, in order to use your ice table, the reason you're using your ice table is to solve for the equilibrium concentrations in terms of X. So that way you can put them into your expression for K. And so this K value is called the equilibrium constant. And the reason for that is because this represents the ratio of your concentrations of all the species in terms of the at equilibrium, right? So these have to be at equilibrium. They can't be the initial concentrations. But as I said earlier, if your X is small, or if the change in equilibrium that you're looking for is so small as to be negligible, then basically your equilibrium concentrations are going to be the same as your initial concentrations. So I just want to get that out of the way. So we're going to take this and we're going to rearrange it. And I'm going to go through step by step to show you exactly how how we can derive the Henderson-Hasselbalch equation. Okay, so I take my equation, my expression here, and I'm going to rearrange it in terms of to solve for the hydronium ion concentration. So I'm going to take the Ka value, right? So, and I'm going to take this, I'm going to rewrite it over here so I can do my magic. It's not magic, it's algebra, sorry. So here we have H3O plus multiplied by A minus, oops, I forgot my equilibrium, EQ over concentration of, oops, HA at equilibrium. And I'm going to do some rearranging. I want the H3O plus to be on this side on top. So what I'm going to do is, oops, excuse me. Sorry about that. My keys got caught on my hand. So here we go. So I want K on top. So I want H3O plus. If I start solving this, I'm going to end up having H3O plus on the bottom. If I divide both sides, and I want to avoid that. So what I'm going to do is I'm going to take the reciprocal of this. So I'm going to have 1 over Ka is equal to the HA concentration at equilibrium over H3O plus at equilibrium multiplied by the concentration of A minus at equilibrium. Okay, so now I can multiply both sides by H3O plus. I'm going to multiply this by H3O plus. And then I want to get K out of here, right? So I'm going to then multiply both sides by Ka. So I'm going to get rid of that. So I'm going to multiply Ka. So multiply here. And notice here that, okay, so this cancels out here. Oh, I should put EQ there, EQ here, sorry. And then I'm going to multiply by Ka over here. So I'm going to write Ka over here. So Ka cancels out over here. And so now I have my hydronium ion concentration on this side. And so if I rewrite that to make that clear, so now I have the H3O plus equal the concentration of H3O plus at equilibrium equal to Ka times the concentration of HA at equilibrium over the concentration of A minus at equilibrium. Sorry, my square brackets are ugly. Let me fix that. Okay, so now I've manipulated my equation here to get this here. So I used algebra to rearrange the equation. Now that I have it in the way that I want it, now what I'm going to do is I'm going to take the negative log of both sides. So I'm going to do that over here. So now I have the negative log of the H3O plus concentration at equilibrium. And now that's going to be equal to the negative log of this huge thing here. So we're going to take the negative log of that. So I'm just going to put this in parentheses. So we have Ka times the concentration of HA at equilibrium over the concentration of A minus at equilibrium. Okay, so now I have this equation here. Now I have to use my knowledge of the laws of logs. So, but before I do that, I'm going to take that -1 out. So I'm going to put this in parentheses. So here I have the negative log of H3O plus at equilibrium. That's going to be equal to, and I'm going to take that -1 out, and I'm going to put that in square brackets. And I'll show you why I do that in a moment. So I'm going to do log of, and then I got Ka times the concentration of HA at equilibrium over the concentration of A minus. Oh my gosh. Calm down, Mr. Cobalt, calm down. Okay. at equilibrium. Oh, I forgot. Close the square brackets. Okay, so now I'm going to apply my knowledge of the laws of logs. I know that, but I want to rearrange this again one more time. Again, I'm sorry, I'm just going step by step so everything's clear. So I'm going to go ahead and rearrange this just a little bit here. So I have negative log of H3O plus equals, and then I got -1, square brackets, and I got the log. Now I'm going to make this a little bit clearer. So then I'm going to have Ka multiplied by the ratio of the HA concentration at equilibrium over the concentration of A minus at equilibrium, and then close the brackets that way. So now I can apply my knowledge of the law of logs. Now, I know that if I have a log of two things multiplied together, then I can separate those by the addition of those logs. So if I have the log of A times B, then that's going to be equal to the log of A plus the log of B. So I'm going to separate those. So now I have the log of negative log of H3O plus concentration at equilibrium is going to be equal to the -1. And I'm going to put this in parentheses. The log of Ka plus the log of HA at HA at equilibrium and over the concentration of A minus at equilibrium, like so. Close the parentheses. Okay, so now I've gone from here to here. Now you're going to see why I have done this step here. So why did I take the -1 out here? Well, now I can put it back in and I can distribute the -1 again. So I just wanted to do that to make it very clear how we're getting this. So now I'm going to go ahead and erase this to give myself some room. We don't need this anymore. Okay, so now I'm going to come over here. So now we have the negative log of the H3O plus concentration at equilibrium is equal to, now it's going to be the negative log of the Ka value minus the negative log, or minus the log of the concentration of HA at equilibrium over the concentration of A minus at equilibrium. Now what I'm going to do is I'm going to take that -1 and write it as a power of -1 there. And the reason for that, and that's another law of logs. So you know that if you have the log of something like the log of A to the -1 power, or whatever power, right? So the of the 2 power, right? That's the same as 2 times the log of A. So you can move the power from here as a superscript to like a coefficient being multiplied. And that's one of the laws of logs. And that works for negative as well as positive powers. And so in this case, all we're doing is we're going the opposite direction. We're taking the number that's multiplied here and then rewriting it as a power. So that's what we're going to do. So we're going to take the -1 and we're going to write it there, but then we're going to replace that with a positive sign, a plus sign. So we're going to now have the negative log of H3O plus at equilibrium equals the negative log of Ka plus the log of the concentration of HA at equilibrium over the concentration of A minus at equilibrium to the -1 power. I know it's kind of getting squished here. Okay, so for my last, well, maybe my penultimate step here is now that I have that -1 there, whenever you have a -1 power or a negative power, well, -1 power, what you can do is you can take the reciprocal of that and turn that -1 into a +1, right? So, so if you have a negative for any power, so this kind of gets distributed to the top and the bottom. So if you have a -1 power on the top, if you bring it to the bottom, that becomes a +1. And then if you have a -1 on the bottom, you bring that to the top, that becomes a +1. So if you just take the reciprocal here, then that becomes a +1, right? So just what I'm saying here is, so if I have A over B, right, to the power of -1, that's the same as having A to the -1 and B to the -1, right? So if I bring this up to the top, that's gonna become a +1, B to the +1. And then if I bring this to the bottom, that's gonna be A to the +1. And then if I take this, basically that would end up as being B over A to the +1. So just kind of showing in gory detail what's going on here. So what I can do is I can just take the reciprocal of that, and that's going to be a +1. So let's go ahead and do that. Like I said, I don't want to skip any steps so that it's very clear how this is being derived using all of the algebra and power rules and all of that at my disposal. So now I'm going to write this as negative log of the H3O plus concentration at equilibrium equals negative log of the Ka value plus the log of the concentration of A minus at equilibrium over the concentration of HA at equilibrium all the way to the +1. But we don't need to write +1, so we can just write it like that. And then for my final step, we understand that what does negative log mean? Well, negative log, anytime you have pH or a negative log, you can put a P in front of the thing that you are taking the negative log of. So I mentioned in another video that if you take pH, you should know that pH equals negative log of the H plus concentration. Well, the H3O plus hydronium ion concentration is the exact same thing as the H plus concentration. It's just that H3O plus or the hydronium ion is a more accurate representation of what's actually in solution, but we shorten it and we say H plus. So we're taking the negative log of H, so that's where we get pH. So the P part of it is the negative log. So here is going to be pH, and that's going to be equal, and look here, we have the negative log of Ka. Well, negative log is P, so that's going to be equal to pKa plus, and then we add this, plus the log of the conjugate base at equilibrium over the concentration of the weak acid at equilibrium. And this, ladies and gentlemen, is the Heisenberg, sorry, not Heisenberg, what am I saying? The Henderson-Hasselbach equation. Heisenberg, what the heck am I talking about? Yeah, so this is the HH equation, or the Henderson-Hasselbach equation. So this is how you derive this equation. Now, you could also derive the equation for the POH equation, which is kind of basically the same thing. So let me show you how to do that. Okay, so let's go ahead and go over the derivation of the other alternative equation related to the Henderson-Hasselbach equation. So in this one here, instead of starting with the weak acid, we're going to start with the weak base reacting with water, and we're going to start with the Kb expression for this reaction, and we're going to derive the related equation to the Henderson-Hasselbach equation. So here we go. So once again, I'm going to do this quickly or more quickly because basically the steps are exactly the same. So I don't need to like show each and every step. So I'll just go through the steps relatively quickly. So I'm going to take this equation, rearrange it. So let me rewrite it down here. So this is going to be equal to the concentration, OH minus concentration over, multiplied by BH plus concentration over the concentration of B, the base. And so here, this comes from this equation here. So here I have the weak base reacting with water to form OH minus concentration, or OH minus, the hydroxide ion, and the conjugate acid. And so now I'm going to rearrange this because now I want the hydroxide concentration on this side. So I'm going to take the reciprocal again, 1 over Kb is equal to the concentration of the weak base over the concentration of the hydroxide ion multiplied by the concentration of the conjugate acid, like so. Now I can multiply the OH concentration on both sides. The hydroxide ion concentration, I'm going to multiply that on this side over here. So that's a negative. So that's going to, oops, canceled out the wrong side. So OH minus concentration. So this cancels out. And now I'm going to multiply by Kb. So I'm going to multiply Kb on this side. And I'm going to multiply by Kb on this side. So Kb cancels out, and now I have the OH minus concentration is equal to the Kb times the concentration of B, or OH, sorry. No, that's B. So Kb times concentration of the weak base over the concentration of the conjugate acid, BH plus. Okay, so now I have this. So again, I'm going to rearrange this. So slightly different, but the steps are pretty much the same. So I'm going to write this up here. So I'm going to have the OH minus concentration equal to, and then I'm going to have Kb times the concentration of B over the concentration of BH plus like that. So before I did this in a later step, but you can do it now. It doesn't really matter. So at this stage here, so now I'm going to take the negative log of both sides. So here I have the negative log of OH minus concentration. Oh, and I forgot, this is all at equilibrium again. So this is at equilibrium, this is at equilibrium, right? So all of this should be at equilibrium. Excuse me for that oversight. So then this is at equilibrium is equal to the negative log of Kb times the concentration of B at equilibrium over the concentration of BH plus at equilibrium. Okay, so very familiar as we saw before. Now I'm going to take the negative log out. So here, or the negative 1, sorry. So negative log of the OH minus concentration at equilibrium is equal to negative 1 times the log of Kb times the concentration of B at equilibrium over the concentration of BH plus at equilibrium. And now I can separate these two. Oops, I forgot to close the square brackets. So once again, I'm going to have the negative log of the OH minus concentration, the hydroxide concentration is equal to negative 1 times, and again, I'm going to separate these two, so it's going to be the log of Kb plus the log of the concentration of B at equilibrium over the concentration of BH plus at equilibrium. And so square brackets. And now I can redistribute the negative 1 to both of these. So now I have the negative log of the hydroxide ion concentration at equilibrium is equal to the negative log of the Kb plus, oops, that should be a negative minus the log of the concentration of B at equilibrium over the concentration of BH plus at equilibrium. Okay, so now let me go ahead and erase this to give myself some room. So now what I can do is I can take that negative, bring that up here, and take the reciprocal again. So now I'm going to have the negative log of OH minus concentration. Oops. OH minus concentration at equilibrium. That's going to be equal to the negative log of Kb plus the log of the concentration of BH plus over the concentration of, oops, that should be, I'm skipping that step. That would be the concentration of B over the concentration of BH plus, and this is going to be to the negative log. Let me get this out of the way since I don't need that. Negative 1. So now I'm going to take the reciprocal of that. That's going to become a positive. So then now I have the negative log of OH minus concentration at equilibrium. Oh, by the way, these should be at equilibrium again. I keep forgetting these are at equilibrium. That's going to be equal to the negative log of Kb plus the log of concentration of BH plus at equilibrium over the concentration of B at equilibrium. And then finally, negative log of the OH minus concentration is POH, right? Because that's what P stands for, the negative log of something. So here is the POH is going to be equal to the PKB plus the log of the concentration of BH plus over the concentration of B at equilibrium. And then here we have the other equation that's related to your Henderson-Hasslebach equation. So if you have this sort of reaction going on here, then you could always use this equation to solve for the POH. And then if the problem is asking for pH, then just use the equation that the pH plus the POH is equal to 14 to solve for your pH. So either way works. Okay, so again, the same criteria apply. One, you can't apply this equation unless one, you have a buffer, and two, the x or the change is negligible for the problem. So that's it for this video. I hope you enjoyed the video. I hope you liked the video. If you did like the video, then please like the video. Hit that like button somewhere down here. Also, subscribe to my channel. Hit that notification bell up there. Share my videos. Also, when you hit that notification bell, you will be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.